Aquiline nose. Often referred to as a Roman nose, the aquiline nose is characterized by a prominent bridge that may curve slightly downward. This shape is historically associated with populations from the Mediterranean, parts of the Middle East, South Asia, and Europe. From an evolutionary standpoint, a pronounced bridge can subtly alter airflow dynamics. The extended internal nasal passage slightly lengthens the pathway air must travel before reaching the lungs. That increased distance allows more time for warming and humidifying inhaled air, which becomes particularly useful in dry or seasonally cold climates where air must be conditioned before reaching delicate lung tissue. The aquiline structure also increases internal surface area within the nasal cavity. The nasal turbinates, curved bony structures inside the nose, are responsible for filtering particles and trapping pathogens in mucus. A longer nasal passage can provide marginal improvements in filtration efficiency. Over generations, in regions with dust-heavy winds or arid seasonal conditions, such subtle advantages could contribute to respiratory resilience. Structurally, the prominent bridge may also provide enhanced skeletal support. Nasal cartilage and bone act as protective architecture for the airway. A more rigid bridge distributes minor impacts more effectively across the facial skeleton. While not armor, skeletal reinforcement can reduce the likelihood of airway collapse from minor trauma. Hidden advantages here lie not in aesthetics, but in biomechanics, airflow modulation, and environmental conditioning. Greek straight nose. The straight nose, sometimes called the Greek nose, features a linear bridge without humps or curves. This shape is frequently seen across diverse global populations and represents a structurally balanced nasal form. The key hidden advantage lies in aerodynamic efficiency. A straight nasal bridge allows relatively laminar airflow, meaning air moves in smoother streams rather than turbulent swirls. Laminar airflow enhances efficient oxygen delivery during moderate activity. When airflow turbulence is reduced, less resistance is encountered within the nasal cavity. This may allow for quieter breathing and efficient ventilation, particularly during endurance tasks such as walking long distances or steady physical labor. The straight structure also tends to distribute pressure evenly across cartilage and bone. Even load distribution can contribute to structural longevity, reducing stress points that might otherwise predispose certain areas to deviation. From an evolutionary lens, a balanced structure often persists because it represents a functional midpoint, neither overspecialized nor limited. It adapts reasonably well across varied climates. Its hidden advantage is versatility, a shape capable of performing adequately in multiple environments without extreme specialization. Button nose. The button nose is small with a rounded tip and subtle bridge. Common across many populations worldwide, this compact shape offers unique physiological benefits. A smaller external surface area reduces exposure to freezing temperatures. In extremely cold climates, minimizing surface area reduces heat loss. Cartilage and soft tissue at the tip of the nose are particularly vulnerable to frostbite. A smaller projection limits exposure and preserves thermal stability. Internally, shorter nasal passages warm air quickly due to proximity to body heat. While longer passages may humidify air more thoroughly, shorter ones heat air efficiently in short bursts of inhalation. This may be beneficial in cold, still air environments where rapid warming is needed before air reaches the lungs. Additionally, a compact nasal tip can be structurally resilient. Reduced projection lowers leverage during facial impacts. The less a structure protrudes, the less mechanical force it absorbs during forward motion trauma. The hidden advantages here center on thermal efficiency, reduced exposure, and compact structural resilience. Upturned nose. An upturned nose features a slightly elevated tip with visible nostrils from the front. Though sometimes perceived purely as an aesthetic trait, it may influence airflow direction. The upward angle can alter how air enters the nostrils, potentially allowing more vertical airflow during upright posture. In humid climates, enhanced air exchange may assist in moisture regulation. The nasal cavity is designed to manage humidity balance. In high moisture environments, airflow that cycles quickly can prevent overhumidification within the airway. From a social and communicative standpoint, nostril visibility can subtly amplify facial expressiveness. The human nose plays a role in micro-expression perception. Slight changes in nasal flare or tip movement communicate emotional shifts. While subtle, improved visibility of nasal movement can enhance nonverbal signaling, strengthening social bonding. Hidden advantages include airflow variation and nuanced communicative enhancement. Hawk nose. The hawk nose resembles the aquiline form but is often more sharply curved and prominent. This shape increases internal cavity volume. Greater internal volume can support stronger airflow during high oxygen demand. Athletes often rely on nasal breathing for endurance training because it filters and regulates air before lung entry. Increased cavity space may accommodate higher air throughput before switching to mouth breathing. Additionally, curvature can create microturbulence within the nasal passage. While excessive turbulence is inefficient, mild turbulence enhances particle trapping. Air that swirls gently increases contact with mucus-lined surfaces, improving filtration. In dusty or pathogen-dense environments, that extra filtration contact can support immune defense. The pronounced structure also reinforces skeletal integrity. Thicker nasal bones may resist deformation. Over long evolutionary timelines, structural durability contributes to trait persistence. Its hidden advantage is airflow capacity combined with enhanced filtration potential. Snub nose. The snub nose is short with a slight outward tilt and broad nostrils. This shape may support rapid airflow intake. Wider nostrils reduce resistance during inhalation. In warm climates where oxygen demand during physical exertion is high, rapid nasal intake supports sustained activity. Broader nostrils also facilitate heat dissipation. During exhalation, warm air leaves efficiently. In hotter climates, effective exhalation assists thermal regulation. Internally, a broader entry allows increased odorant molecule intake. The human sense of smell depends on molecules reaching olfactory receptors high within the nasal cavity. Wider nostrils may slightly increase scent sampling efficiency, which historically could assist in detecting food, smoke, or environmental threats. Hidden advantages here revolve around airflow speed, thermoregulation, and olfactory sampling. Nubian nose. The Nubian nose is characterized by a longer bridge with a wider base and broader nostrils. Commonly observed in parts of Africa and the African diaspora, this structure is strongly associated with adaptation to hot, humid climates. Wider nostrils facilitate greater airflow volume. In warm climates, the body prioritizes cooling through breath exchange. Efficient intake and release of air supports heat regulation. Humidity influences nasal structure evolution. In moist air environments, extreme humidification is unnecessary because ambient air already contains moisture. Wider passages allow efficient breathing without requiring prolonged conditioning time. The longer bridge still provides filtration surface area. Combined length and width create a balanced system of volume and conditioning. The hidden advantage is optimized breathing efficiency in warm climates, balancing airflow speed with adequate filtration. East Asian low bridge nose. Often described as having a lower nasal bridge and rounder contour, this shape is common across East Asia. A lower bridge reduces protrusion, minimizing cold wind exposure. In northern Asian climates with strong seasonal winds, reduced projection limits tissue freezing risk. Internally, rounded nasal cavities can preserve humidified air effectively. The structure may maintain stable internal moisture levels, protecting mucosal lining from cracking in dry winter air. Another hidden advantage lies in structural flexibility. Less pronounced cartilage projection can absorb impact differently, distributing force across broader areas of the midface. Its benefits emphasize environmental wind resistance, moisture retention, and balanced structural distribution. Wide nose. A wide nose features expanded nostril width and broader alar base. This shape maximizes airflow intake. In environments where physical labor, heat exposure, or high pathogen density are common, rapid airflow supports both oxygen delivery and immune filtration. Increased surface exposure inside the nostrils allows more mucus contact with inhaled air. Mucus traps pathogens, dust, and pollutants. Greater surface area means more immune interaction before particles reach the lungs. Thermally, a wider opening assists heat exchange during exhalation. Warm internal air meets cooler external air, facilitating passive cooling. The hidden advantages are oxygen throughput, filtration efficiency, and climate-adaptive ventilation. Narrow nose. A narrow nose typically features slim nostrils and a thinner bridge. This shape is often associated with colder or drier climates. Narrow openings restrict rapid cold air influx. Slower airflow allows more time for warming and humidification. In dry climates, controlled airflow reduces internal moisture loss. The nasal cavity must preserve hydration to protect mucosal membrane, narrower passages, slow evaporation, maintaining protective mucus layers. Additionally, restricted airflow increases contact time between air and nasal turbinates. This improves temperature conditioning before air enters the lungs. The hidden advantage is air moderation, slowing, warming, humidifying, and protecting respiratory tissue in harsh climates. Bulbous nose. A bulbous nose features a rounded, fuller tip due to thicker cartilage and soft tissue. While often discussed cosmetically, this structure may provide cushioning protection. The soft tissue mass at the tip can absorb minor impacts, distributing force before it reaches delicate internal structures. Cartilage density also reinforces airway openness. Structural thickness can prevent collapse during forceful inhalation, such as during strenuous exercise. Maintaining airway patency ensures consistent oxygen flow. The fuller tip may also contain a rich blood supply. Enhanced vascularization assists temperature regulation, warming cold air quickly as it passes through. The hidden advantages lie in shock absorption, airway stability, and thermal conditioning. Crooked or deviated nose. A nose with a slight deviation or asymmetry may seem purely structural, yet asymmetry can subtly alter airflow pattern. Mild deviation may increase airflow on one side while reducing it on the other. Alternating nasal dominance, known as the nasal cycle, is a natural physiological rhythm where one nostril becomes more open while the other partially constricts. A slightly asymmetrical structure may enhance this cyclical airflow shift. The nasal cycle supports immune health by allowing one side to rest and rehydrate while the other handles airflow. Alternating dominance maintains mucosal health and optimizes filtration recovery. While severe deviation can impair breathing, mild asymmetry may actually diversify airflow contact patterns within the cavity, improving particle capture in varied regions. The hidden advantage is dynamic airflow variation and immune rhythm support. Flat nose. A flatter nasal profile with minimal projection reduces exposure to environmental extremes. Reduced protrusion lowers frostbite risk and decreases injury leverage. Internally, flatter profiles may maintain consistent humidity within the nasal cavity. In high humidity climates, less protrusion means shorter air travel distance before lung entry, which can be advantageous when conditioning demands are low. The structure emphasizes compact resilience and minimized environmental vulnerability. Its hidden advantage centers on reduced exposure and structural efficiency. Pointed nose. A pointed nasal tip extends slightly forward with defined cartilage shaping. Increased projection lengthens the air channel marginally. As air travels further, it experiences additional conditioning, warming, filtering, and humidifying. A defined tip can also direct airflow downward slightly, optimizing inhalation angle during upright posture. Small aerodynamic changes can influence breathing comfort during movement. Cartilage definition often correlates with structured septal alignment, which may assist in stable airflow patterns. The hidden advantages include conditioning enhancement and directed airflow optimization. The human nose as an adaptive instrument. Across all variations, the nose functions as a climate regulator, filtration system, immune gateway, and airflow modulator. Shape differences represent subtle environmental calibrations accumulated across generations. No structure is inherently superior. Each reflects adaptation to humidity, temperature, altitude, wind, pathogen density, and physical demands. Your nose warms air to body temperature, humidifies it to protect lung tissue, filters harmful particles, houses immune defense cells, supports smell perception, influences vocal resonance, and shapes facial expression. Its external appearance reflects internal airflow engineering shaped by ancestral geography. Every curve, width, projection, or contour changes how air behaves before entering the lungs. Slight variations alter turbulence, conditioning time, filtration surface area, and thermal exchange. Over thousands of years, small physiological efficiencies compound. Your nose shape is not random. It is environmental memory written in cartilage and bone. It carries adaptive echoes of climate, migration, and survival strategy. Keep learning. Keep embracing what makes you unique. Subscribe and explore the science that makes you extraordinary.